Okay, Assalamualaikum and good day everyone. Right, so now we are going to proceed with our next topic, generalization of the elementary problem. Okay, so remember previously what we have done is find the extremal by using Euler's equation, right? Where the Euler's equation is Fy minus derivative of Fy prime with respect to x equals to 0. Okay, so now we are going to proceed with the same problem where we want to find the extremal, but now we want to make it as a general. Okay, that's why it is called as generalization of the elementary problem. All right, so before this we have a functional of before this we have a functional of f, x, y and y prime. So in order to find the extremal of this f, we implement the Euler's equation. So now we are going to have types of functional. Okay, all right, so the first type here is a functional dependent on higher derivative. All right, so before this, what we have done is f, x, y prime. Okay, in terms of higher derivative here, now suppose we are given a functional in the form of a functional j here is in terms of f, x, y prime until yn. Alright, so previously what we have been doing here is until f, x, y prime. So we stop until here, right? Okay, now we are going to identify this y up until yn prime. Okay, where f is an n plus 2 times differentiable function with respect to all argument, yx is in the class C of x0, x1 with the boundary condition given y prime, yx1, y prime x1 until given by n minus 1 here. Okay, depends on how many order that you have. Alright, so instead of stopping until the first order here, where we use Euler equation, now what if that functional have up until y up to the nth order? Okay, so we modify this Euler equation and finding the extremal by using Euler-Poisson equation. Still, this Euler-Poisson equation comes from the Euler equation where that Euler equation is the first variation where we derive the first variation from increment, right? So same process. Okay, but now in this Euler-Poisson equation, we have up until y to the power of n order. Alright, so this Euler-Poisson equation is actually quite general here because if we use this Euler equation, what if we have order n equals to 1? The order n equals to 1. So that's why we have here Fy minus, plus minus 1 to the power of 1 d1 dx to the power of 1 Fy prime equals to 0. So basically, the Euler's equation that we have discussed earlier comes from this general equation of Euler-Poisson, where if you rewrite this, it can be dx of Fy prime equals to 0. So basically, this is the general form of Euler-Poisson equation where if that n equals to 1, we come back to this Euler equation that we have used earlier. Okay, so this Euler-Poisson is used for functional dependent on higher derivative. All right. Okay, now let's take a look at this example. Okay, we have a functional g equals to integrating of 360 x squared y minus y double prime squared dx. So here we have a functional. Okay, so here we have a functional consists of x, y, y prime, y double prime, even though it has no y prime, but it is the order, right? So for this case, we can use this Euler-Poisson equation up until n equals to 2, where from here, when n equals to 2, your Euler-Poisson equation becomes Fy minus derivative of x Fy prime plus this squared, the x squared of Fy double prime, okay, equals to 0. So same process. We identify what is our f, where f here equals to 360 x squared y minus y double prime squared. And then according to this Euler-Poisson equation, we need to find our Fy. Okay, our Fy is 360 x squared, and then we have our Fy prime where there is no y prime here, so Fy prime equals to 0 and Fy double prime equals to minus 2y double prime. So substitute in the Euler-Poisson equation here. So we have 360 x squared, okay, minus Fy prime is 0 plus d squared dx squared of minus 2y double prime, okay, equals to 0. Right, so now we are going to solve this. We have 360 x squared minus 0 minus 2 d squared dx squared of y double prime equals to 0. So solving this, okay, solve this in order to find what? To find our extremal in terms of yx here. So our extremal must be in terms of yx because the functional is given by jyx. So we need to solve this to find our yx. Okay, so now from here we have del squared d squared dx squared y double prime equals to, so differentiate y double prime twice will give you y quadruple prime, all right, equals to, you divide with 2 here, 180x squared. Okay, so how can you find y? So for this case, you just can integrate one by one, right? Okay, so y quadruple prime of x here equals to 180x squared. So y triple prime should be integrate 180x squared with respect to x. Then you have, right, okay, right. So now we are going to solve this, right? So we need to integrate one by one. Okay, so integrating y to the power of 4 will give you y triple prime. Okay, so this is your integration product here. And then integrating of y to triple prime will give you y double prime. Integrating y double prime will give you y prime. Okay, and integrating y prime will give you yx. So you need to integrate one by one here. Okay, I like to give you the general solution. You can try after this. Integrate one by one. Okay, where the extremal of this problem is given by yx, half of x to the power of 6 plus c1 x cubed plus c2 x squared plus c3 x plus c4. And then apply the condition. So the given condition for this problem here is y naught equals to 0, x equals to 0, y equals to 0, x equals to 0, y prime equals to 1, x equals to 1, y equals to 0, x equals to 1, y prime equals to 2.5. Okay, so now you find the general solution first of extremal yx here. Apply the condition. Okay, and then your last answer of extremal should be yx equals to 1 over 2x to the power of 6 plus 3 over 2 x cubed minus 3x squared plus 1. So this is direct integration only because it involved with y quadruple prime only. There is no constant, there is no second or third derivative inside the function. So we just have to integrate one by one and don't forget the constant part. Okay, for each of your integration process. All right, you may try this. Okay. Okay, so we have done with Euler. Okay, remember in Euler equation, we find the extremal of f, x, y, and y prime, right? And then we got Euler Poisson equation, where we solve up until nth order. Okay, where the n here will be determined, the Euler's Poisson equation here will be determined by how many times is your order. Okay, so as for the previous example, we have up until second order, so we just substitute n equals to 2. Now, we have functional dependent on m function. Okay, instead of how many order, now we have how many function. So the functional dependent on m function here. Okay, numbers of function. All right, as you can see here, a functional j now consists of y1, y2 up until ym. Previously, we have a functional j of yx. Just like in our previous lesson, also a functional j of yx. Now, for this functional dependent on m function, we have how many function up until m function? y1, y2, function 1, function 2, function 3, up until m function, where that function consists of f, x, y1, y2, ym, y1 prime, y2 prime, up until ym prime. Okay. So for this case, at least twice differentiable with respect to all its argument and with a boundary condition in the form of yk equals to ykx naught equals to yk naught, ykx1 equals to yk1, k until m. So how many k depends on how many function m there. Then the extremal, how can we find the extremal of this kind of functional is given by a system of second order differential equation. So instead of only Euler's equation, now we are going to use a system of Euler's equation. So a system of Euler's equation is applicable for a functional j of y y1, y2 up until yn. Okay, where the f here consists of x, y1, y2, y1 prime. Let's say we have two functions, y1, y2 prime, right? So if we have until three function, we are going to proceed y3, y3 prime. Four function, y4, y4 prime. Okay, now in order to find the extremal, we are going to have a system of Euler's equation. So instead of finding the extremal of yx only here, now we can find the extremal y1x, y2x until ymx. So there are many extremal that we can obtain from this kind of function. Okay, now let's take a look at this example. So here we have a functional j consists of y and z, two function. Okay, how many function? Two function. So now from here what we can see that your f must consist of x part. Okay, y and y prime, z and z prime, where it is equals to y prime squared plus z squared plus z prime squared. Now we have two variables. Okay, remember this k depends on m, where m is how many function that we use. So now we have two function of y and z. So our Euler equation should be in terms of fy, okay, equals to 0. Fy minus derivative of fy prime with respect to x equals to 0. And another Euler equation focusing on z. Fz minus derivative of fz prime with respect to x equals to 0. So we have two Euler equations. Solving this means we solve the system of Euler's equation. So remember, we still focusing on finding the extremal, but depends on what type of extremal that we want to find. Just like previously in our last class, we have a functional consists of f, x, y prime. Then we just find the extremal by finding the solution of Euler's equation. Now we have the first type of up until nth order. So we have the general of Euler-Poisson equation. We substitute the value of n. Now we have the functional dependent on m function. So since we have two function in this example, we have two types of Euler equation. Depends on depends on y and z function here. So from here, you need to identify what is your fy, fy prime, fz, fz prime. All right. So from this example, we just can find our system of Euler's equation here. So for the first part, what is our fy? Fy here equals to 0. Okay. And then our fy prime should be 2y prime equals to 0, which give you here the differentiate 2y prime will give you 2y double prime equals to 0. Then another one, fz here equals to 2z, right? And then minus differentiate fz prime 2z prime equals to 0. So from here you have substitute 2z minus 2z double prime equals to 0. So now you have first equation, first equation of differential equation, second equation of differential equation. So you need to solve one by one, all right, one by one of these two equations and find your extremal in terms of yx and zx. Okay, I hope you can try, can understand this, I think, because we just use Euler equation, but now we have system of Euler equation where it depends on each function of y or z, right? Okay, I hope you can try this and obtain yx equals to c1x plus c2 and zx equals to c3 exponent to the power of x plus c4 exponent minus x. Try find the values of c1, c2, c3 and c4 by using the boundary condition given, and your yx should be equals to x and your zx equals to sine x minus 1 over. All right, try this. I hope you can try this. I'm not going to give every step here because I believe all of you can do this, right? The process is similar, but the difference here is how the Euler equation is represented. Depends on the types of functional given. But our focus is to find the extremal. How can we find the extremal? Based on the functional. Either it is one functional consists up until one order of x, y, y prime, and then we have up until nth order, or we can have many functions in that one functional. So depends on the condition, but our focus is always to find the extremal. So the way we find the extremal is always similar. All right. Okay. Last type here, the next type here, the functional. Okay, what the functional here dependent on functions of several independent variables. Okay, instead of having m function, right? M many function. Let's say previously we have functional g of uh, y, x, z, x, right? But now we have one function, but with several independent variable. So here we have only one function z, but in z involved with independent variables of x and y. So how can we find the extremal of this type of functional? Okay, so as you can see, when the functional here is given by a function of having two variables, let's say for this example, two variable x and y. So the f function that is given by consists of x, y, the independent variable x, y, z, and then we have zx, we have zy. Okay, just like before, we have a functional of yx. So we have x, y, and y prime, right? Now we have a functional of z, x, and y. So the variable is x, y. So that z here consists of zx. Sorry, z first. The function z itself, okay, and the first derivative of z with respect to x and the first derivative of z with respect to y. If we have up until nth order, then depends on the Euler Poisson. Right now, just focus on the regular one. So we just focus on the numbers of independent variable. Okay, so this is the functional, consists of two variable, and the function given by the function given is involved with the variable itself and the derivative of z with respect to the independent variable, where we call it as the partial derivative. Okay, we differentiate partially according to x and y. So that's why f here is a 3 times differentiable function of x argument, right? We differentiate z itself by differentiating z with respect to x and with respect to y. The assumption here, we thought a function z is in terms of x and y. So in order to simplify the process, we just put z there, but we know that function z is in terms of x and y, which is continuous, having continuous derivative up to order 2 inclusive in the domain D. Assume on the boundary L of D here yields an extremum of the functional. So we can find the extremal of the functional. So if the extremum of this functional is realized on the surface Z, then the function Z satisfies the Euler-Ostrogradski equation. So if we have a function depends on two independent variables. Now, in order to find the extremal, we use this Euler-Ostrogradski equation, where fz minus del fp del x minus del fq del y, where what is del fp del x and del fq del y. Okay. So this is just a simplified version of the total partial derivative here. Okay, according to this, we can just simplify to this Euler-Ostrogradski equation. As you can see, del fp del x and del fq del y are total partial derivative with respect to x and y respectively, where del fp del y consists of fpx plus fpz del z del x plus fpp del p del x plus fpq del q del x. Okay, where as you can see here del z del x equals to p and q. All right, so to simplify this, okay, it's quite confusing here because it consists a lot of variables. So to simplify this, all right, if the derivative of z up to order n appear under the integral sign, then the Euler-Ostrogradski equation becomes, all right, so now if the derivative of z up to order n appear under the integral sign, so we have the integral sign here, right? So now the Euler-Ostrogradski equation becomes like this. So we are going to use this, all right? Okay, now let's see. Let's try this example. The previous equation here only consists of elaboration on the partial derivative. Okay. But we involve in the integral sign, then we use this. All right. So how can we use this? So first, we need to identify the functional. Okay, let's take a look at this example. The functional j now involved with z, where z involved with two independent variables of x and y. Okay, so from this, as you can see here, the functional z, x, and y here can be written as, okay, to make it seems simpler, del squared z del x squared can be rewritten as z x double x squared plus z double y squared plus 2zxy squared minus 2z f dx dy. So from here, in order to use any Euler, we always come to f, where our f here is given by this, right? Z double x squared plus z double y squared plus 2z squared xy, sorry, 2zxy squared minus 2zf. Okay, and according to this function, okay, our Euler-Ostrogradski equation must be in terms of fz minus del fzx, okay, minus del fzy del y plus del squared del x squared fzxx, okay, plus 2 del squared del x del y of fzxy, okay, plus del squared del y squared of fzyyy. Okay, because we have up until second order, that two variables of second order. So we stop until f del squared del y squared of fzyy equals to 0. So according to this Euler-Ostrogradski equation, we identify what is our fz. Okay, looking at our f there, we differentiate of f here with respect to z. Okay, what is our fz? Which is negative 2f. What is our fzx? Equals to, there is no zx, equals to 0. What is our fzy? There is no zy, equals to 0. Right? And then fzxx, where it equals to 2zxx. Right? fzxy equals to 4zxy, right? And then fzyy equals to 2zyy. Okay, so we have all of these coefficients. Now we just substitute to our Euler-Ostrogradski equation. All right, so from here we have negative 2f, okay, minus del x of 0 minus del y times 0 plus del squared del x squared of 2zxx, okay, plus 2 del squared del x del y of 4zxy, okay, plus with 2zyy, del squared del y squared, okay, del squared del y squared of fzyy, which is 2zyy equals to 0. Okay, so solving this one by one, as you can see, this should be 0, this should be 0. So what left? What's left? Negative 2f. And then here we have z double x, right? And then we differentiate it again twice with respect to x. So we have 2z x plus 4 times 2, 8z xy. So we have xxyy, and then we have del squared, we have 2z double y, again differentiate with respect to y twice, so z y equals to 0. Okay, in terms of differential, we can write this as 2 del to the power of 4z del x to the power of 4 plus 8 del to the power 4z of del x squared del y squared plus 2 del to the power of 4 z over del y to the power of 4 equals to 0. So this is how can we write the Euler-Ostrogradski equation of the functional? It is quite hard for you to find the functional of, the extremal of zxy here. But now we just want to find the Euler-Ostrogradski equation which is obtained by this functional given, right? So I hope you can try the example given in the notes, right? Where it involved with depends on how many order, okay, or how many function, right? And also how many independent variables, okay? So don't forget, we still want to find the extremal just with the different types of functional given, right? Okay, so I think that's all for this chapter. You may try first. You have to try it by your own, understand it first. If you have problem, you can ask me, okay? All right, thank you guys. Assalamualaikum.